Okay, on section 2.3, you should be able to explain the relationships between set operations and logic connectives, the properties of set and logic operations, and Venn diagrams to sort and reason with data. So the first thing we're going to look at is section intersection. So intersection is a lot like the AND operator in the logic from the first section. So it says consider the following sets. C is equal to X such that X is a college graduate. S is equal to X such that X earns at least $40,000. Suppose we want to mail a questionnaire to all individuals in a certain city who are college graduates and who earn at least $40,000. Then the individuals to receive the questionnaire include both those common to both sets, C and S. So they have to be in both sets, right? So the intersection would look a little bit like this in the Venn diagram. C again is college graduates. S is those making greater than $40,000, or people that make greater than $40,000. So the intersection would be college graduate that makes at least $40,000. So over here in S, you could have some people that do not or are not college graduates, but they make at least 40,000. And over here, you can have some college graduates that don't make at least 40,000. But in the middle, you have college graduates that make at least $40,000 a year. So the intersection of the two sets, A and B, is written like this: A and then like a horseshoe, and then B is the set of all elements common to both A and B. So it's all elements that are in both sets. Okay. So here are some examples. So here's A, 1, 2, 3, 4. B is 3, 4, 5, 6. So A intersection B is 3 and 4. That's what they both have in common. B, A is equal to 0, 2, 4, 6, 8, so on. Even numbers. B is the odd numbers. So A intersection B is actually equal to the empty set. So remember, the empty set means there's nothing in there. So that means that A and B are disjoint. And then finally, C is 2, 4, 6, 8. And B is 1, 2, 3, 4. So the intersection of A and B is equal to A, is equal to these. Because all of these here, all of these that are in A are gonna come out in B. So when you intersect them, it's really just the 2, 4, 6, 8 even numbers, because the even numbers are gonna come out in B also. So that's just a simpler way to write the intersection of both there, okay? So it says if C represents the individuals with a college degree and S represents individuals earning at least 40,000, we can use a Venn diagram to display this information. If we know that 4,800 individuals or 4,800 individuals have college degrees, so in this circle C should add up to 4,800, and 5,400 earn at least 40,000, and 1,200 have a college degree and make 40,000. So you can split it up in this way. Just make sure that your addition makes sense. So for C, you should have 4,800. For S, you should have 5,400. So you subtract the 1,200 from the 5,400, and that gives you just the ones that are in S but not in C. And same thing for the other one. Subtract 4,800 minus 1,200, and that gives you 3,600 that are not in the intersection there. Okay, so that is called set union. Okay, so now the union of two sets, it's bringing them both together. So this is the difference. This is different from intersection. So if you look at this picture here, this is the union. You're putting everybody together. Okay, so you're gonna have some overlap there, right there. You're still gonna have that overlap where they're both in C and S, but union is kind of like the OR. So union of two sets A and B is A, and then the horseshoe but upside down, or with the opening up, more like a U for union. A union B is the set of all elements in A or in B. So we're putting everything together, right? We're combining in this case. So here I have 1, 2, 3, 4, 3, 4, 5, 6. You combine them, you get 1, 2, 3, 4, 5, 6. 0, 1, 2, 3, 4, 1, 2, 3, and then the even and then the odd. So then you have basically all numbers, including all whole numbers, because you're including 0, and so on. Okay. And again, A union B is equal to B. In this case, it's equal to B because B contains all of these. All of these are in B, so it's basically just B. Okay. Now the set difference is when you want the set of, like in this case, the complement of C relative to S, or the set difference of S and C, the difference. Okay, so the complement, the complement of A relative to B, written A minus B, is the set of all elements in B that are not in A. So basically, you're just getting the difference between the two. You're getting the ones that are not right in there. So B minus A is all of these over here that are in B, but not in A. So that would be the union of B and the complement of A. Okay, so let me see, the complement of A. Hold on. Let's see, trying to get this. So the complement of A is everything that is not in A. So it would be everything out here, right? All this, even I'm going to color over there green, so it might turn a different color. I don't know. So all of this, but I still have to stay inside the box, right? So this is the complement of A. What is not in A? That's the complement, right? And then you're going to intersect it with B. So that means you're really just talking about this green part, right? So again, that's B union the complement of A. So basically, it cannot be an A. It cannot be an A and only in B. So that's why this part that they shared is not included. Okay, so then here's some examples. If DEF and A is equal to DEF, B is equal to ABCDEF, C is equal to ABC, then A minus B, so this one and this one, you're taking everything in A that is not in B. Well, B includes everything in A. So that means there's nothing that is in A but not in B. Over here, backwards, what is in B but not in A? Well, those first three, right? A, B, C. Here, what is in B but not in C? So since this is A, B, C, D, E, F is not in C. So that's what your answer would be. And then if you do vice versa, C, A, B, C, what's in C but not in B? Well, nothing. It's the empty set. All right. So there's commutative properties for this. So for all sets A and B, again, this is the intersection. A and B is the same thing as B and A, or and also A or B is equal to B or A, or A in union B is equal to B union A. The orders are commutative. So if you remember your operations, commutivity means you can switch them, right? You can do one first and then the other. Like for example, addition is commutative. 3 plus 4 is 4 plus 3. Subtraction is not commutative because 3 minus 4 is not 4 minus 3, right? Associative property, you can do kind of the same thing. For addition, you can do in parentheses here first. You can do this first, and then whatever you get from here, you can intersect it with A, or you can do intersection of A and B and then intersect it with C. For union, same thing. You can do BC and then intersect with A, or AU, AB, and then intersect with C. The order of that is irrelevant. Just like addition, you could do 1 plus 2 plus 3. You could do 1 plus 2 first and then plus 3, or 2 plus 3 and then plus 1. The order doesn't matter. So associative property of these set operations for the intersection and union, they're associative, just like addition. Again, not subtraction. Distributive property of your intersection over the union. So here's union, so we call it over because it's going over that. So you would do A intersection B, and then union A intersection C, right? So it's sort of like you're distributing it over this, okay? So let me show you. Let me just make, I want to make the notation of it, or just show it to you what I'm talking about. Okay, so again, we're going over that one, so it's going to be A intersection B, right? That's how you get this part, and then union this union, and then A intersection C. So that's how you get this one, right? So that's how that works. Okay. All right. So here are some examples. It says use set notation to describe the shaded portion of the Venn diagrams. So here, what's going on here, you're taking the union, right, of both, so everything together, but then you got to subtract that middle part, right? So you get all of this all together, so that's going to be A union B. So that would include the middle part, right? But when you do the minus, right, that's how you subtract that middle part. That's one way to do it. The other way to do it is to do A union B again, and then you intersect with the intersection of the complement of A, B. So that means it would be all the outside. Okay. So these are different ways to write it. Or you could do A minus B, so it's this minus all of this. So that would cut out this part. Union with B minus A, so it would cut out this part from the second one, and then you put them together. So you get this and this. And then here's the second one for this one. These are, a little complicated, but you can sort of work your way through it a little bit. What is this saying here, right? That means A intersection B. So where do they intersect? So here and here, it's talking about this one, right? And then B and C, right here. And then you're joining those two. We're going to put together. Or it says B intersection with A, so B right here. And then it's going to intersect with A union C. So these two. And then so you're just left with those green parts. Here's some more examples, and I'll let you kind of sort through those for the sake of time. If you have questions, you can always ask me on Pronto. Okay, so suppose M is the set of students taking math, E is the set of students taking English, identify students described in each. So region A, what is region A? That's the students taking math, but they're not taking English, right? Region B, students taking math and English, right? Both. And then C is students taking English but not math. And then what are students over here in D? Students in D, they're not taking either math nor English. They're out here. So that would be the complement of this union, right? You color all this in, both circles color them in. The complement of that then would be outside of the circle. So it'd be in here, right? Let's see, can I copy this? It doesn't matter. And then it's the union, the intersection of the complements. So it's out of that side of here and outside of this one, and you just join them. Okay. So I'll let you work through this example. In the PowerPoint, it says in a survey and they investigated, there's 110 college freshmen. The following information gathered: 25 took physics, 45 took biology, 48 took physics, and then you have some. Here are the intersections, right? Physics and math is 10. 8, biology and math. 6, physics and biology. 5 took all 3. So at the inner, right there in the very inner, you should see that 5 that took all 3, right? And then physics and you should be able to see the rest. As you fill them in, you're gonna probably be able to get the other ones, the ones that are missing, right? Like this number, I think, wasn't coming out there. So 5 is the one that they're taking all 3. This one right here is taking both physics and biology, but not what's it, math? Not math, right? So you can kind of 14. So 14 is taking physics only, and so you can kind of fill in the numbers, and you'll see. You can kind of like from just addition and subtraction, you can figure out the rest. Okay. So you have several examples. So they just walk you through these examples. You can pause it if you need to look at it a little bit more. All right, and the last thing we're going to talk about is Cartesian products. So another way to form sets from 2 sets, or to produce a set from 2 sets, is to form pairs of elements. Okay, so it's very simple. I mean, you've heard of the word Cartesian, kind of like the XY plane, the Cartesian plane. So it's pretty much the same thing. So it says, suppose a person has 3 pairs of pants, blue, green, white. So I kind of talked about this in the last video. And 2 shirts, blue and red. According to the fundamental counting principle, there's 6 ways, right, to make a pair, an ordered pair. So it would look something like this. On the, kind of say, in this case, it's the pants axis. You got blue, white, and green. And on the shirt axis, you got red and blue. So in this first spot right here, it's an intersection of blue and blue. Right here, it's going to be blue and red, white and blue, white and red, green and blue, and green and red. So it's a good way to kind of see all the possibilities. If you have more than 2 choices, then it's going to get complex, right? You're going to be into the 3rd dimension or 4th and so on. Equality for ordered pairs. So xy equals mn if and only if the first components are equal and the second components are equal. So it's kind of very obvious, right? If x is equal to m and y is equal to n, then the 2 ordered pairs are the same ordered pair. You're talking about the same thing, right? So for any set of sets A and B, the Cartesian product of A and B is written as A. It should be an XB. If this should be an X. I don't know why it didn't come out. So the first component of each pair is an element of A, and the second component of each pair is an element of B. All right, and you basically have to go through all the possibilities. So you have, let's say, A, B, C, and then 1, 2, 3. So then A cross B is A1, A2, A3, and then B1, B2, B3, and then C1, C2, C3. If B comes first, then the number needs to go first, right? 1A, 1B, 1C, and then 2A, 2B, 2C, 3A, 3B, 3C. If it's crossed with itself, then it's AA, AB, AC, BA, BB, BC, and then CA, CB, CC. So they do the order of the ones like the XY, if you can think of it as a coordinate plane, it does matter. So the first one has to go first, the second one goes second. And so that's why A and B in this example are different, right? So it is possible to form a Cartesian product involving the null or empty set. So suppose A is equal to 1, 2, because there are no elements in the empty set, no ordered pairs XY with X belonging to A and Y belonging to the empty set. So A cross the empty set is equal to the empty set. So basically, you can't make ordered pairs because the second one didn't have anything, right? It's the empty set. So how are you going to do, how are you going to make a pair? There's no second element to make a pair with. All right, so similarly, the empty set cross A is equal to the empty set for all sets of A. So this is just saying if you're going to cross something with the empty set, with something that's empty, then you're going to get an empty set. There's not going to be anything in there, okay? So work on that section, and if you have any questions, message me on Pronto.